Hello everyone. In this video, we're going to use what we've learned so far about statistics to actually do some statistical inference. And we're going to begin with hypothesis testing. So now we've established how much we might expect our sample mean to deviate from the true mean. That's the standard error of the mean, which we discussed in the last video. That's our expected kind of the typical size of the difference between our sample mean and the true mean. And if we typically expect the sample mean to differ from the true mean purely by random chance, by an amount equal to the standard error, then if we see a difference between our sample mean and our assumed true mean that is significantly larger than the standard error, then we have some evidence that maybe our assumption of the true mean is not a very good assumption. And that's essentially the essence of hypothesis testing. So we're going to introduce a formal hypothesis testing framework. But I don't want to get too bogged down in the formal details and lose sight of the intuition, which is, if I tell you that the average employee in the United States without an advanced degree makes $70,000 a year, you might say, all right, let's assume that's true. I'm going to go out and collect some data. But if I find that the average is significantly different from 70,000, then I'm going to say you're wrong. And we establish how big is significantly different by comparing that difference between the average you find with your sample and the assumed truth of 70,000 by comparing that difference to the standard error. So, first, we are going to so we know from this prior study that employees with advanced degrees in the U.S. make $70,000 a year. This is something that we just know from a prior study. In practice, we won't necessarily know this to be true, but we will assume some value for the true mean of whatever situation we're talking about. In this case, we're going to make what's called a null hypothesis. And this is the thing we're assuming to be true. That employees without advanced degrees also make an average of $70,000 a year. So we don't need to base it upon this prior knowledge. We could just assume some average salary for people without advanced degrees. But it makes some amount of narrative sense for me to say, I'm pulling on my prior knowledge of people with advanced degrees. Let's just assume there's no difference. Maybe, degrees make no difference. So we'll just assume that they make the same amount. So we assume that mu, the true mean, going back way earlier in the notebook, we assume that the actual average salary of people without advanced degrees is $70,000 a year. So we've now assumed a value for mu, the true mean. And that assumption is called our null hypothesis. The other thing we have to do, if we're going to settle this argument, is set a threshold for a significant difference as our standard of evidence? Do you need to find a sample mean that's 2 standard errors away from our assumed mean? 3 standard errors? In practice, what we'll usually do is say we will choose a probability called alpha that is typically small, and it's the probability that the difference we observe between the sample mean and the true mean, or the assumed true mean, the null hypothesis, is due purely to random chance. We want this probability to be small because we know the sample mean will probably be different from the null hypothesis, purely by random chance. But we want, if it's different, what we're interested in is differences that aren't due to random chance. So if we demand that that probability be small, then probably the difference is attributable to some real, interesting, significant cause rather than just random chance. So we choose some threshold of evidence called alpha. You'll often see people choose an alpha of 5% or 1%. Those are just conventions. Don't choose alpha based on the fact that people say, oh, you should choose alpha of 5%. You should choose, if you're doing hypothesis testing, you should choose a threshold of significance that is appropriate for the question you're asking. Physicists working in particle physics demand something like a 1 in a trillion chance of their observation being due to random chance. That is their threshold of evidence. 1 in a trillion. But if you and I are just having dinner together and we're having a little disagreement and it's no big deal, but we decide that we're going to, put our argument to the test, maybe we only need a 10% threshold or a 20% threshold, and we'll call that good enough. So you should choose a threshold of evidence that's appropriate for your situation. So we're going to encode our null hypothesis in Python by setting the variable mu to 70. So we've assumed that the true salary for people without advanced degrees is $70,000 a year. Now that we have established the parameters of the argument, the null hypothesis, and the threshold of significance, now it's time to collect some data. So you go out to challenge my claim that people without advanced degrees in the U.S. make $70,000 a year on average. You collect a sample of salaries of people without advanced degrees, and you collect 100 salaries. And you find that the sample mean, or the mean salary in your sample is $61,000, or $60,900, or $60,940. Close enough. 61,000. Keep in mind, you might get a different number here than I do, because this is a random sample. And if I run this again, I will get a different number. So 66,000. So here, let's stick with this 61,000 ish number, similar to the first one I drew. So we now have a difference, right? You collected data, and you found a sample with a mean salary of $60,000. So we have a difference of $9,500 here per year. The next thing we have to do is compare that difference to the standard error. So we'll compute our difference between our sample mean, x bar, and our assumed true mean, mu. And we already know that's $9,500, $9,500. And then we'll divide by the standard error. So that's what's in this denominator here. Sigma divided by the square root of n. That's the same formula we had up here, just with the square root carried through, so the square root cancels with this square, and then applies only to the square root of n. So, for the moment, what we'll do is, there's more to be said here about how we calculate this sigma, the standard deviation of the individual salaries. But for the moment, we're going to simply estimate that sigma from our sample. And there's a whole lot of extra discussion here that I am not going to discuss. If you know statistics, then you know at this point I should be talking about the student T distribution and about unbiased estimators of the standard of the variance and all that kind of thing. I'm not going to talk about any of that because, quite frankly, that's more advanced than what we need to know right now. What we need to know right now is that we want to compare the difference between our sample mean and our null hypothesis mean to the standard error. So I calculate the standard deviation from my sample, and I divide by the square root of my sample size. And that quantity is called a z-score. So I'm going to define z equal to the difference between my sample mean and mu divided by my standard error. So this gives me a z-score of negative 1.74, or 5 if you're rounding. What can we do with this z-score? What does this z-score tell us? Well, first of all, it tells us that our difference between the sample mean and the assumed true mean was 1.7 times larger than the standard error. So that's already some useful information. If the standard error is the kind of deviation that we would typically expect between the sample mean and the true mean, then we know we've exceeded to some degree that expectation, right? This z-score is greater than 1. It's more than we would have expected. Now, is 1.7 a lot? Is that way more than what we would typically expect? It's hard to say. So what we're going to do is now calculate a probability and compare that to our threshold of significance, alpha. So at the beginning, we decided some value for alpha, say 10%, because this is just like a maybe a wager that we've made over dinner. And the way we calculate a probability from this z-score is using the central limit theorem. So remember, the central limit theorem tells us the distribution we would expect of sample means for a particular sample size. If my sample falls somewhere in this distribution, say over here, we can use the central limit theorem distribution, which we do know because we can calculate it. The central limit theorem tells us what it should be. We can calculate a probability from that z-score using that central limit theorem distribution. And I'm going to do that in code, and then I'll show you visually how it's done. So in code, we take a normal distribution, a standard normal distribution, and our probability is simply going to be the cumulative distribution function for our z-score. So we get a p-value of 0.04. The p-value is the probability of observing this average salary, or one that is even more different from our null hypothesis, purely by random chance. So there was a 4% chance that we would have observed a z-score of 1.7 or larger. Or expressed another way, there was a 4% chance that we would observe, purely by random chance, a sample salary or a mean salary that differed from our null hypothesis by as much as it did, or even more. So there was a 4% chance we'd observe that difference, or a more extreme difference, purely by random chance. Now, 4% is pretty small. That's smaller than our 10% threshold for significance. So you might say, hey, I went out, I collected 100 salaries. The average was $60,500, and there was only a 4% chance that I would observe that big of a difference from 70,000 only randomly. And I would say, all right, well, that's less than the 10% chance we had agreed on before, so you must be right. It must be that people without advanced degrees make less than $70,000 a year. And that would be the conclusion of the hypothesis test. You found evidence that was significant because the probability that you would have observed it purely by random chance was smaller than the threshold we agreed upon in the first place. Now let's dive in a little bit into how this p-value is calculated. Here I have two very similar graphs shown on just two different scales. On the first scale, we have on the x-axis salaries. Critical region, I want to be actually slightly different. So I'm showing here a 5% critical region at the moment, but then I said 10%. So I want to update this to be consistent with a 10% critical region. So let's see, SP stats norm, and here I want PPF 0.1, so I need 1.28. I'll call this C, and then I will say C equals SP stats norm PPF alpha, and we'll set alpha equal to 0.1. There, oh, that's not quite right. There we go. And I need to update it in this lower plot as well. So here we have C, negative C. There we go. Okay, so now these plots are updated to be consistent with a 10% threshold. So what do we see in these plots? This first one has an x-axis displaying salaries. Our null hypothesis was that the true average salary of people without advanced degrees was $70,000. Assuming that's true, the central limit theorem tells us our sample mean should be distributed according to a normal distribution, centered on $70,000, and with a standard deviation equal to the standard error of the mean, which we calculated according to the formula that we saw in the previous lecture video. We found a sample mean over here. If we were to shade the 10% critical region, that would start over here at about $63,000 and extend off to the left. So 10% of the probability under this curve corresponds with this red shaded region. This the area under this curve, total area, is 1. And the red shaded region has an area of 0.1. To calculate the p-value, we would look at the area under the curve to the left of this blue bar for the sample mean. So that 0.04, that 4%, is the amount of area to the left of this blue line. And that's simply that's all there is to calculating the probability. It's just the area under the curve of this given by the central limit theorem distribution that is starting at our sample and then moving in a direction that is more extreme, that differs more extremely from our null hypothesis, where the central limit theorem is centered. This bottom plot that looks almost identical just has a slightly different x-axis. Here, we plot the standard normal distribution, centered at 0, with a standard deviation of 1. The z-score corresponds with the sample mean scaled to the scale of the standard normal distribution. So our z-score was minus 1.7. 4% of the probability under, or area under this curve is to the left of that blue bar. So we can see these are two identical plots plotted on different scales. So the z-score is simply a rescaling of our sample mean relative to the standard normal distribution. So that's a picture of how hypothesis testing works, how we calculate z-scores and use those to calculate p-values. In the DW mini project, we ask you to calculate z-scores for a couple different questions. So this lecture may be useful to reference back to when computing those z-scores, particularly when thinking about how to compute the standard error in the denominator of the z-score. Remember, the standard error is the difference we would expect to see between the sample mean and an assumed true mean. In the next video, we're going to wrap up our discussion of statistical inference by talking about parameter estimation and confidence intervals.